Greetings. So let's continue with the math part. And so in the previous video we just became interested in, I call them prefixed point of the function TP, because I call that the assignment U was a model of the program P if and only if TP of U is a lower bound of U. Now, viewing this from a more generalized viewpoint, so let P be a poset, not a program. This capital P is now for posets. In this video we won't use programs. Okay, so let P be a poset. For example, the poset of assignments, if you want to give it a concrete application. So we oppose it, and f being a function from P to itself. So in the previous video, the function TP was such a function which mapped the poset of assignments into itself. So in that case, P was 2 to the z and f was TP. Okay. Now the element x of the poset is called, so there will be 1, 2, 3 different definitions. First is a prefixed point of f. The second will be a postfixed point of f, and the third definition will be a fixed point of f. Now, chances are you already encountered at least one of these guys, most probably the fixed point. Fixed point of f. And what are the definitions? So, if f of x is lower bound of x, now that's the thing which we are seeking for, because there was a statement that the function, that the assignment U is the model if and only if TP of U is a lower bound of U, so that's the same. Postfixed point is just the other way around. And we got postfixed points during our iteration. In the previous video, if you remember, we started by a constant 0, and after a one-step some of these guys get increased, and after the second iteration some of the other guys also get increased, so TP just mapped them higher and higher. Yeah, so in the very first iterations we had post-fixed points, and in the last iteration we had an actual fixed point which states equality between these two sides. Of course, this means that a fixed point is, so x is a fixed point if and only if it is a post-fixed point and a pre-fixed point as well. Yeah. Now, okay, so we are very interested in finding prefixed points. Good. Now, of course, if the poset P has a least element bottom, then no matter what f is, we clearly have that the bottom element is smaller than or equal to the f of bottom, because the bottom element being the least element is smaller than or equal to anything. So no matter what f of bottom is, bottom will be a lower bound, so bottom is a postfixed point, always, of course. Of any f. Now the interesting thing is if we just have some conditions on f, then we can do more. One such condition is being monotone. So the f function, and in this case function f, and in this case it doesn't have to be a p2p function, it can be a p2q function where p is a poset and q is another poset. It can be the same, but it don't have to coincide. And the definition is monotone if x being smaller than y in P, so these are elements of the input poset, implies f of x being smaller than or equal to f of y. Now this will be a very, very central notion regarding functions mapping posets to posets. And we will eventually prove that the function tp is monotone as well. Currently we don't have that, but it's quite intuitive, because if an assignment sets a body to 1, then if you just increase the value of some variables, then this body will still be 1, because being 1 means that it only contains variables which were already set to 1 in the first assignment. And if you set some zeros additional to 1s, then the body still will be 1, which means that its head should be set to 1 as well. So basically that's sort of proves that, for example, the function tp is monotone. If you have a greater assignment, then the result will be also greater or equal to assignment as well. Now, why it's important that the function is monotone is because of that. So there's the definition, and there is a statement that if f p2p is a monotone function. Now in this case we have a p2p function because we want to talk about fixed points. Post fixed point is a monotone function. And x is a post fixed point of f. Post fixed point of f, then so is fx. So is f of x. So if you have a monotone function, then post fixed point will remain post fixed point as well. Now let's just prove this. X is a post fixed point means that x is smaller than or equal to f of x. And from this we can apply that if x is smaller than or equal to y, then f of x is also smaller than or equal to y. So I just apply f on both sides and the relationship will be preserved. So this means that f of x, I'm just applying f on both sides, f of x. And this is exactly the statement that f of x is smaller than or equal to f of x. So if f is monotone and x is a post fixed point, then f of x is also a post fixed point. And then f of x is also a post fixed point, and so on. So f will just make a chain of post fixed points if you just iterate it. So it means that if x is a post fixed point, then f of x is larger than f. But since now f of x is also a post fixed point, we get that f of x is also a post-fixed point. So this is again smaller than or equal to f of x, and I will just denote it by f to the third of x, and so on. So we will have a chain of post-fixed points, which is great. So each of these guys are post-fixed points if f is monotone. So this is a so-called chain This is a chain of post-fixed points of f. Post-fixed points of f if f is monotone and x is a post-fixed point. Of f, of course. Yeah. Now in particular, because we already know that bottom is a post-fixed point, this means that, right, bottom is a post-fixed point. So here we have that if f from P to P is monotone, and P has a least element bottom, then it means that we can start iterating f from the least element bottom, and we will just get some sort of an increasing sequence. And if you just recall what happened when we just iterated the TP function, this is exactly the same process. We just started by the constant 0 assignment, and then we just computed the next one. In each step we just applied with the same function TP to our current assignment, and we just iterated, and we had an increasing sequence of assignments, because in each step we just set more of the variables to ones, and those guys which were already set to ones were just preserved. So f square and so on. This guy is a chain of post-fixed points of f. Now this seems to be interesting because this is exactly the same process which we already done for the TP function, post-fixed points of f. Now that's great. Oops. Advertisement and stuff like that. So if we have a least element, then this guy is a chain of post-fixed points of f. And remember, we are just trying to get a prefixed point. Now, the interesting thing is that first I should tell you what a chain is. So you might have some impression what a chain is, of course, but I should define this formally. So if x, P is opposite, then x, a subset of P, is let's define this by arranged as a chain of P if each pair of the elements are somehow comparable with an x. So if for any pair xy we have either x smaller than y or y smaller than x. Yeah. Now in the above case we have a chain because, well, they are linearly ordered, and if you just pick two of them, then the one which has a larger superscript of f, so f of 0 is smaller than or equal to f of 1 of bottom, is smaller than or equal to f of 2 of bottom, and this is smaller than or equal to f of 3 of bottom, and so on and so on. So basically they are totally ordered, linearly ordered. So by so it's also you can also say that it's a linearly ordered subset of P. Subset of P. That's a chain, and so a totally ordered subset of P. Now, the interesting thing is that you have this chain and you want to find a prefixed point. Now the thing is, each and every prefixed point of this function f is an upper bound of this chain. So that's also a statement. So basically this says that you are just increasing those postfixed points, and all the prefixed points are just somewhere above you during the word process, above or equal. So the statement is that if say y, and so prefixed points are interesting because we are trying to find them. So find a prefixed point of TP, of the TP function, is the main task that we are just trying to shoot for. So if this y is a prefixed point of f, then I say that this whole chain is a lower bound of y, and I can write this as follows: f to the n of bottom, with n being at least 0, is a set. So this is just the set of the elements of the chain. So bottom, f bottom, and so on, they are all in this set, and no one else is the lower bound of y. Basically, we will eventually prove that this supremum of this set, if it exists, will be the least prefixed point of f under some specific circumstances. So if f is a so-called continuous function, then we should just take the supremum of this chain, which is basically the same thing as taking the limit of some convergent function in real analysis, say. So let's prove this. Proof. So we will just show that we show that for each n, f of n, f to the n of bottom is smaller than or equal to y, if y is a prefixed point of f. Now if I want to show something for all the non-negative integers, then it, well, might be done by induction, and this is exactly the same. So for n equals 0, we have f to the 0 of bottom, which means that I will apply the f on bottom 0 times, which means that I will get bottom, and of course this button is smaller than or equal to y, because y is an element of the poset P whose least element is the button. Now if n is, so for n plus 1 we have that f to the n of button is smaller than y. That's the induction hypothesis. Now f is monotone. I should have stated that, so of course f is still a P2P monotone function, of course, because this chain exists as being a chain only if f is monotone. At least we stated that only for that case, but here I can apply the monotonicity of f, and I just get f of f to the n button being smaller than or equal to f of y, right? Now this guy here is just f to the n plus 1 of button, and that guy f of y is smaller than or equal to y because y was a prefixed point. And now, because this relation smaller than or equal to is transitive, we get this f to the n plus 1 of bottom is also lower bound for the very same y. So we prove this to 0, and based on that we already know this for n, we just prove this for n plus 1, which means that from 0 we can deduce 1, from 1 we can deduce 2, from 2 we can deduce 3, and so on and so on. Yeah, induction we are probably familiar with it, and this means that each and every prefixed point is an upper bound of this chain, which is just the iteration sequence of f starting from the bottom. Now that's fine, because it says that every prefixed point is an upper bound of this iteration sequence, which means that it might be worth to study the supremum of this chain, if the supremum of the chain exists. Now the thing is, it won't exist in any possible poset, in an arbitrary poset, but there is a definition, of course, tailored to exactly this use case, namely poset P is a complete partial order which is a different thing as being a complete lattice, by the way. So it's a complete partial order, or CPO, complete partial order, if all the chains of P have a supremum. All the chains of P have a supremum. So you don't have to be able to compute all the suprema of subsets of P, but if you have a chain, then it should have a supremum in order to be a CP. Now in particular, since 0 is a chain, the empty set is a chain because, yeah, so it's an empty chain, all the elements of the empty set are comparable, yeah, that's fine. So the supremum of the empty set should exist, should exist. And the supremum of the empty set is always the least element of the poset, which means that in a CPO there is a button. Exists in a CPO. Right, okay, so from this point on, if I have a CPO, then I can start anything from the bottom element of the CPO, because in a CPO, bottom element always exists. Now it will turn out that for example, the poset of assignments is a CPO. So if I state anything regarding CPOs, then it will be true for the poset of assignments as well. Now, this means that there is this iteration sequence bottom, F bottom, FF bottom, FFF, F to the fourth, F to the fifth of bottom, which is a chain. And if this happens to be in a CPO, in a complete partial order, then I can take the supremum. But the supremum of a monotone function, or monotone function's iteration sequence, won't be always a prefixed point. I need one more definition for that. But in general, a monotone function's iteration sequence's supremum is not necessarily a prefixed point. Remember, we are still trying to find prefixed points. Okay. And the very last definition I need to state something regarding this. So at the end, I will try to prove that under very specific circumstances, the least prefix set point of this function f can be computed as the supremum of this iteration sequence we just described. And this specific circumstances is that we have to be in a CPO, and the function should be a so-called continuous function. And that's the last definition I will just sketch now. So a function f mapping a poset to a possibly other poset is continuous if for each non-empty x, non-empty chain of P, here non-empty is important, non-empty chain x of P such that the supremum of x exists, basically this is almost the same thing as a convergent sequence in real analysis. So if you want to have an intuition about the supremum and chains, then it might be insightful just to reformulate this part as follows. A function p is continuous if for each sequence of real numbers f having a limit, the supremum is the limit, okay, such that f of exists, it holds that the application of f and the application of supremum is swappable. It holds that, so the function applied to the supremum should be the same as, so we are just computing the images of each element and then we just take the supremum. Now this right hand side supremum happens in Q because the images are already in Q, so So this is a subprimum of a set of elements of Q. So continuity means that you can just swap the function application in the subprimum operator if the input is a chain having a subprimum. Okay. Now, the first thing, so TP will be a continuous function. We will prove it in some other video because this part is only for math, but later on we will prove that the function TP is a continuous function. So basically every notion we just introduced in this video, monotonicity, continuity, CPOs, prefix and postfix points, iteration sequence, this will all be applicable directly to the scenario from the previous video where we had the function TP acting on assignments, as in the dispositive of assignments. Okay, now there is a statement that these two notions are not entirely independent because a function, if f from P to Q is continuous, then it is also monotone. And f is also monotone. Okay. Now, let's just prove this. Continuous function is always monotone. Okay, so at this point it might be a good thing to note that the notions of reorganization are not exactly the same as the notions of opposite theory. Because this statement doesn't make any sense in the setting of reorganization because their monotonicity is a completely different notion. Okay, so proof. Okay, so assume that f is continuous. So okay, we have this, and we should prove this f is monotone. So and let x being less than 5 be members of P. We should show that f of x is smaller than or equal to f of y, because that's the definition of monotonity. So we should prove f of x being the lower bound of f of y. Okay. But for continuity, I have to have a chain, right? Now, if x is smaller than y, then in particular fxy is a chain, right? Is a chain. Because in order to be a chain, I have to each pair of the elements should be comparable, but it's exactly what's written on the left hand side. So x is always comparable to x, y is always comparable to y, and x is smaller than y or equal to y because that was the initial assumption, so the condition from which we should use f of x being a lower bound for f of y is a chain. Of course, it's non-empty because x is there. And actually it has a subprimum, namely y, because y is a lower bound of x, y is a lower bound of itself, that's fine. And of course, if there is any other upper bound set of this set, then this upper bound will be an upper bound for y as well, because y is in the set. So if you have a set with greatest element, then of course the greatest element will be always the subprimum of this set. Non-empty with y being the subprimum of x and y. Actually, these two things are equivalent in this way. So, because if you have a set of at most two elements, which is a chain, so you have Yeah, so you have two elements, and you know that the supreme of these two elements set is one of the elements. Then it means that this guy is of the greatest element of the set, which means that it's an upper bound for the other element. So it's an if and non-if part. But the thing is that this is exactly a statement of shape for which I can apply continuity. Because if you just recall that continuity meant that if I have a finite, if I have a non-empty chain x of p, then there exists with an existing supremum, that's fine. Then I can just swap the application of supremum and the function application, which means that so f of y is, because of this part, this is the same as f of supremum of xy. Now that's the same because f being continuous, so f being continuous, I can just swap the f and the supremum. So it's just the supremum of the f of these two guys, fx and fy. And now again, what do I have? I have that f of y is the supremum of a set in which there is the f of x, and of course the supremum is an upper bound for each and every element of the set, which means that f of x is a lower bound for f of y, because the supremum is always an upper bound for any element of the set. In particular here fy, the supremum is an upper bound for f of x, which is an element of that set. And we are ready because, yeah, so this is exactly which we should prove in this case. So if we have a continuous function, then it is also monotone, which means in particular that if you just start to iterate a continuous function from bottom, f bottom, and so on, then it will be a chain of elements. And now we have a theorem. Theorem, so-called Tarski fixed point theorem. The Tarski fixed point theorem which says that if f from p to p you want to iterate, then the target poset should be the same as the source poset is continuous, and the supremum say x star of the set bottom, f bottom, and so on, exists. So for example, if p is a CPO, then it will exist because if the function is continuous, then it's monotone. If it's monotone, then this sequence is a chain. And if it's a chain in a CPO p, then its supremum exists. And then x star is the least prefixed point. Now we are talking prefixed point of f, and it's also the least fixed point. as well. So what this theorem says that is, and an application of the theorem says that if you have a CPO in which you have a continuous function, then its least fixed point can be computed by starting from the bottom, iterating this f, computing the supreme of this chain, and that's all. And you will get the unique least prefixed point of f. Now this will be exactly the case of the setting of the TP function. So basically this will be the method which can define the canonical semantics of a logic diagram. So let's prove this. For this proof, okay, so proof. First we know that, we already know that this guy here, so f to the n button n at least 0 is a chain, and also that every prefixed point is an upper bound. Each prefixed point of this set of f is an upper bound of this set. Of this set. Now the second, which we already noted, is that, remember, if x is smaller than or equal to y, then x is smaller than or equal to the supreme of x is smaller than or equal to y. There was a statement with this. Yeah, so we have such a statement if the supreme exists, but the statement of the theorem explicitly stated this if the supreme exists, right? And this is x star, so it means that x star is a lower bound for each and every prefixed point. And of course, where y is the set of the prefixed points of f. And of course, because every fixed point is a prefixed point as well. Remember, a fixed point is a point which is both a prefixed point and a post-fixed point. So all the fixed points are actually prefixed points as well. So if x star is a lower bound for all the prefixed points, then of course x star is a lower bound for all the fixed points as well. So although x star is a lower bound for all the fixed points, so basically, if we can prove that x star is a fixed point, then it will be a fixed point which is smaller than or equal to all the other fixed points, which means that this will be the unique fixed point, unique least fixed point of f, and it will be a fixed point which is a lower bound for all the prefixed points. So because if it's a fixed point, it's a prefixed point as well, it will prove that x star is the unique least prefixed point of f as well. So we only have to show that x star is a fixed point. We only have to show that x star is a fixed point. Well, okay, let's do this. So so this means that I have to show that x of x star equals x star. Now, just substitute the definition of x star. So x star was the supremum of the iteration chain. Okay, so f of the supremum of the iteration chain, and being an integer. Okay, now since f is continuous, and this guy is a chain here, a subprime of a chain, so the image of a subprime of a chain is the same as the subprime of the image of the members of the chain. That's the definition of continuity, so it is the same as the subprime of f of members of the chain, f to the n button, and at least 0. Now this means that instead of applying f0, 1, 2 and so on times, I will apply f1, 2, 3 and so on times. So I can just write this as f to the n plus 1 button, and that's the 0, or I can write this as the subprimum of f of n of button, but n ranging from 1 to infinite. Now what's this? F of button, the subprimum of the following set, f of button, f second of button, f third of button and so on. The only thing which is missing from the original iteration sequence is the lowest element, the least element button. But there was a statement about that. The statement stated that if the subprime of x is always the same as the subprime of x plus the bottom element. Now this is exactly the same situation, so I'm just writing here some comment, then adding bottom does not change the subprime, and there was a statement regarding that. I think it was 2 videos before. So, and if I add the button, then I basically add f of to the 0 of button. That's button, right? I apply f0 times. So this is the same as the subprime of f to the n of button, with n being at least 0, because from 1 and upwards this is the original set, and for 0 it is the button. Now, and this is x star. So we just get the f of x star, which is this guy here, is exactly x star. So the subprimum of the iteration sequence is a fixed point f if f is continuous and this subprimum exists. So basically that's it. This means that this Tarski fixed point theorem gives us a very powerful way to compute the unique least prefixed point of f. So what's left? For logic programs, first we can show that 2 to the z is a CPO, and second, the function tp is continuous. Because in that case tp will be a continuous function from 2 to z to 2 to the z, and since the p will be a CPO, then the subprime of this chain will exist, And in that case, the subprime of the chain will be the least prefixed point of the function tp, and a prefixed point is exactly what the model of the program p is, which means that this is exactly the way how we should define the semantics of a logic program if we can show these two things, that two results that CPO and TP is a continuous function. But since both of these statements are about logic programs, I'll just tell you these in another follow-up video. Till then, bye bye.